2.5-inch full-range driver, custom TPA3128 amplifier, Qualcomm Bluetooth with aptX codec, custom control board with BMS, 9.6 amp-hour battery. Hi, I'm Greg, and this is GR Craft Lab. The main goal was to make a small, fully 3D printable Bluetooth speaker based on a full-range driver from one of the well-known brands. After making some simulations in WinISD, I decided to go with the Seas Orbit FL8 model with aluminium con, as it seems to work very well and even play some bass in a little box with a volume of just above 1.2 liter. The next step was to design a custom power control module. I used an mAh 328p. I know it's a little bit overkill, but it's cheap, you can buy it almost everywhere, can work with voltages well below 2 volts, and at power down mode drives less than a few microamps of current. In a combination with SLM6600 3-amp charging IC makes it a perfect solution for a battery management. I wanted to use the TPA3128 amplifier IC from Texas Instruments because it's a very good sounding and battery efficient Class D chip. I needed a board as small as possible, but still have film capacitors at input, good reconstruction filter, and differential inputs to eliminate any noise from the Bluetooth module. I wasn't able to find any ready-made board, so I also decided to design a custom one. I picked up a Qualcomm's QCC3008 Bluetooth module with aptX codec, cause it's a huge gain in quality compared to a cheap SBC models. The most important thing is that I can use a dedicated programmer to set up everything. From the name displayed in the phone's Bluetooth device list, to a baffle step compensation and some EQ tweaks in built-in DSP. Also it has differential audio outputs, so I don't need to care about any noise problems. And the last part of the puzzle, the battery. I used the LG MH1 18650 lithium-ion cells connected in 1S3P configuration, so I should get voltages from 3 to 4.2 volts depending on the charge status of the battery and about 9.6 amp-hour capacity. Then the power control board will let me charge the battery through a USB-C socket to about 4.2 volts and also shut down the speaker when the voltage falls down below 3 volts. And that's it, let's get to the build. So the enclosure consists of a few parts. The base, USB bracket, battery clamp, front, sides, and the grills. The front will be glued to the base, but first I need to secure the sides with the masking tape. Next step is to mount the USB-C socket to the bracket and attach it to the base. All the parts require some type of sealing at the joints to make sure that the whole enclosure will be airtight. Here I'm using Monacore MDM5. It's a self-adhesive foam for speakers. Now it's time for the battery. The cells are brand new, but anyway I always like to check that the voltages are similar. When everything is okay, I also glue the additional insulators. After a restrictive quality check, I can begin with the spot welding. Now it's time to solder the control board and the amplifier. I'm using solder paste and a hot plate to put it all together. Unfortunately, I don't have stencils for those boards, so the process will be a little more time consuming, but those boards are so small that it should be fairly easy. Not using stencil almost always results in a few solder joints, but fortunately it's easy to repair those with a flux and soldering iron. After assembling the board, I uploaded the Arduino sketch to the microcontroller and started the power consumption tests. Pressing the power button for about 2 seconds turns the speaker on or off. When the power is on, I measured less than 6 mA of current consumption and about 1 microamp in the off state. Quick view on the amplifier assembly. And it's time to test the amplifier. From the left I have a 12 volt power supply, an AC RMS voltage meter, a scope, and a 4 ohm resistor. There is also a sine wave generator set to 1 kHz at the bottom. The resistor is connected to the output of the amplifier, and the generator is our source. Now I will slowly raise the signal level at the generator and watch the scope to see where the amplifier starts to clip the output sine wave. Now watch the scope till you see flat edges at the top and the bottom of the waveform. This indicates clipping. After reducing the signal a little bit, the meter shows 7.68 volts RMS. Square that, divide by 4, and this gives almost 15 watts of clean power. I'm using a TPS 61088 DC boost converter set to 12 volts to power the amplifier. This tiny board with 4 LEDs will display the battery charge level. Next, I need to prepare the Bluetooth module. I'm starting by soldering the SPI programming header. Next pins are for the power supply and audio output. This cable will connect Bluetooth audio output to amplifier input. And here's a little close-up at the Seas full range driver. Now I will install the control board and the boost converter at the top of the battery bracket. Finally, it's time to install the battery inside the enclosure. Now I'm mounting the amplifier to the backside of the enclosure. Bluetooth is mounted on the top wall so that the antenna is above the rest of the electronics. The power switch is sealed by a rubber ring, while the LEDs are glued to the front. And finally, it's time to mount the speaker. I'm also using the sealing foam to make sure that there will be no air leaks. Now the side panels and the ceiling foam again. Passive radiators are made out of a 3D printed disc glued to a soft rubber surround. It's time to play with the passive radiator's weight to get their quite low frequency response. I made up a simple adapter so I can connect the speaker directly to USB pins and then through a USB plug straight to an impedance measuring jig. I'm using a free software called ARTA to measure the impedance of the speaker. This is the first impedance response graph taken with no additional weight on radiators. There are two peaks. The dip between them is the enclosure tuning frequency. I know from simulations that I need a value of around 65 Hz. Now it's about 94 Hz, so I need to add some weight to the radiators to lower this value. I used washers and a double-sided tape and take another measurement. With this mass added, now it's about 76 Hz, still too high. So after messing around, I found that a weight of about 11.4 grams will give me the best results and a tuning frequency of about 64 Hz. Now I can permanently glue the weights to the radiators. Before I close the box, I will make some changes to the Bluetooth module. To do this, I need to connect the SPI programmer. First, I will change the name of the speaker. Since the speaker doesn't have a microphone, I will turn it off and also disable the low power audio codecs. The last thing is to set up the DSP. Since the speaker works in mono mode and the amp is connected to the left output, I have to mix the stereo input signal and route it to the left channel. Also, I set the high pass filter to 40 Hz to protect the driver from the lowest frequencies. In the EQ section I apply slight compensation for the buffer step effect and a little boost for the highest frequencies. Apply all the changes and disconnect the board. Finally, I will just add some damping material and the speaker will be ready to use. So I'm very happy with the results. The sound is crisp, full of detail, while still not being fatiguing during long listening sessions. The bass is also better than I expected. I can't wait to use this tiny driver in a stereo project in the future. Thanks for watching and see you soon.